Hello everyone, we are the Group 7 and our topic for this presentation is about stress, strain, elasticity, and proportional limit. Let me introduce you to our speakers. This is Uziel Rivera from Britannia, Renero Reyes, Olimar Licos, and Althea Saison.
We, the Group 7, would like to thanks to Dr. Sarosa and Dr. Gracia for giving us this opportunity to make this presentation. We hope that you will enjoy the presentation we have made.
Hi everyone, my name is Althea Saison, and today I will be the one to present the first topic of our group, which is stress. So the stress that I will be talking about is not the stress that I am currently feeling now. So what is stress? Stress is the force per unit area within a structure that is subjected to a force or pressure. So it is the internal resistance to applied external force that causes an object to undergo a certain change. So the change may be sometimes a change in movement, direction, or geometrical construction. So this is the formula that we follow or we use when we want to look for stress. The F stands for force applied and the A stands for the area on which a force is acting. So when we later on get the answer to this, the unit of measurement that we follow is megapascals or MPa. How do we explain stress? So when a force or pressure is applied on an elastic solid, the atoms or molecules respond in some way at and below the area of loading. But the applied force has an equal and opposite reaction at the area at some other point in the structure. In order to further understand stress, we are going to talk about stress distribution or stress gradient. This term is the pattern wherein the stress induced near the surface decreases with distance from the loading point, and it increases as the supporting surface is approached. So if you look at the two pictures, the elastic solid's atoms may be compressed in such a way that their interatomic equilibrium distances are decreased temporarily until the force is decreased or eliminated. So in the first picture, there is force applied on top of the elastic solid, and if you see it closely, the interatomic and intermolecular forces are compressed because of the applied force. However, in the second picture, as the force is lifted or as the elastic solid goes back to its original state, the interatomic forces and intermolecular forces are also adjusted back to their original state. However, if the force is increased further, it is possible that the atoms will be displaced permanently or their bonds ruptured. So in relation to stress distribution, dental restoration should be designed such that permanent displacement of atoms or rupture of interatomic bonds does not occur except possibly at surface areas where normal wear may occur. Now we will talk about the four classifications of stress, which is tensile, compressive, shear, and flexural or bending stress. The first one is tensile stress, and this happens when two sets of forces are directed away from each other in the same straight line. So this is caused by a load that tends to stretch or elongate a body. In layman's terms, this stress happens kung may ginabutong pang-isa ka object towards two different directions. The second one is compressive stress. This happens when two sets of forces are directed towards each other in the same straight line. This is caused by a load that tends to compress or shorten a body. The next one is shear stress, and this occurs when two sets of forces are directed parallel to each other but not along the same straight line. This may also be produced by twisting or torsional action on a material. So basically, shear stress happens if, for example, one part of the object is pushed to the left side and the other part of the object is pushed to the right side. The last one is flexural or bending stress, and this can produce all the three types of stresses in a structure, but in most cases, fracture or breakage occurs due to the tensile component of the object. So here we have several examples of the application of stress in real life. So the first one we have is its application in engineering. Next, we have car towing, regular office work such as cutting, sitting, hanging of clothes, and other daily activities, sports like tug of war, and of course, the gym equipment whenever we go to the gym. For its application and relevance in dentistry, there are many fields such as prosthodontics, orthodontics, surgery, and implantology that involves the concept of stress.
Hi there, I'm Yulimar and I will be the speaker for the topic strain. So what is strain? Strain is defined as a change in length per unit length when stress is applied. Strain is simply the measure of how much an object is stretched or deformed. Strain occurs when force or stress is applied to an object. Strain deals mostly with the change in length of the object. Next is we have here the formula of strain. Strain is represented by the symbol epsilon. In order for us to get the strain, the change in length or delta L should be divided to the unit original length. And we should always remember that strain is expressed as a percentage. Strain may be either elastic, plastic, or a combination of either elastic and plastic. Elastic strain is reversible. Strain disappears when force is removed, while plastic or ductile strain represents permanent deformation of the material which never recovers when force is removed. Strain has three classifications. We have the tensile strain, compressive strain, and shear strain. Tensile strain. Tensile strain is defined as a deformation or elongation of a solid body due to the application of a tensile force or stress. In other words, tensile strain is produced when a body increases in length as applied force tries to stretch it. Next is we have the compressive strain. Compressive strain is the fractional decrease in length of an object due to a compressive stress. And lastly, we have the shear strain. Shear strain is the ratio of displacement to an object's original dimensions due to stress, and is the amount of deformation perpendicular to a given line rather than parallel to it. Relevance of strain in real life. Molding or crafting of glass, application in industrial field, lifting of things using a cable of crane, application in the field of engineering. And lastly, we have the application of strain in dentistry. Strain can be used in fixed prosthodontic clinics. A sticky candy like a sticky or gummy candy can be used to remove crowns by means of a tensile force, resulting to a tensile strain when patients try to open their mouth after the candy has mechanically bonded to the opposing teeth or crowns.
Modulus of elasticity. So what is elastic modulus? It describes as the relative stiffness of material, which is measured by the slope of the elastic region of the stress-strain graph. It is also the stiffness of material that is calculated as the ratio of the elastic stress to elastic strain. So its property is that the elastic modulus is an intrinsic property of a material. At a fundamental level, elastic is a measure of the bond strength between atoms. The greater the modulus, the stiffer the material and the smaller the strain. So the equation for elastic modulus is calculated as elastic equals stress over strain. So as you can see above, previous lessons where stress is equals to applied force over cross-sectional area and the strain is the change in length over original length. The three classification of elastic modulus. So the first is the Young's modulus, is a mechanical property of linear elastic solids such as rods, wires, and other similar objects. Other values such as bulk modulus and shear modulus can be used to determine materials' elastic characteristics, but Young's modulus is the most often utilized. Next, we have the shear modulus. It is calculated by measuring the deformation of a solid caused by applying a force parallel to one of its surfaces, while an opposing force operates on the other surface and keeps it in place. Consider shear as a force that pushes on one side of a block, with friction acting as an opposing force. Lastly, we have the bulk modulus. It is a measurement of a substance's capacity to tolerate volume changes when compressed on all sides. It's calculated by dividing the applied pressure by the relative deformation. Next, application in real life of elasticity. Examples are it determines the material stiffness. It describes how stress and strain interact in a material. It describes how much a material may stretch or shorten under tension or compression. Next, application in dentistry. Example is the principle of elastic recovery. Let's say a burnishing of an open material margin, where a dental abrasive stone is rotated against the metal margin to close the marginal gap as a result of elastic and plastic strain. After the force is removed, the metal springs back to an amount equal to the total elastic strain. Another example is the impression material. Let's say the impression materials should have a low modulus of elasticity to enable it to be removed from the undercut areas in the mouth.
Hello, I'm Renero Reyes Jr. from DDM3C and I will be your speaker for this topic. Proportional limit. The magnitude of stress above which plastic deformation occurs. As stress is increased, the strain is also increased. In this graph, the value of stress is A. The red line represents the highest strain at which the stress-strain curve is a straight line. Below the proportional limit, there is no permanent deformation in a structure. Example, the object will return to its original dimension when force is removed. From initial 0 to point A shows that stress is proportional to strain. The material below the proportional limit is elastic in nature. Relevance of proportional limit in real life. Stain can be caused in fixed prosthodontic clinics. A sticky candy can be used to remove crowns by means of a tensile force, resulting to a tensile strain when patients try to open their mouths after the candy has mechanically bonded to opposing teeth or crowns. This may help in replacing old and weak tensile strength of the said dental materials.
Yippee! So that's all the topics we have shown. I bet you have learned something from this topic. Thank you for listening.